sound within enclosure. So, sound within enclosure is slightly different than what we have looked in open. See, if you see, this is an auditorium. Now, this is the source, this is the source, this is the source, and let us say this is my receiver, this there could be another receiver, etc. I mean, just to explain what is a sound within an enclosure, we have taken this. So, what will happen is direct sound comes there, but there can be reflection, there can be reflection, and if you see this source, how many reflection? This reflection, this reflection, this reflection, and there can be some reflection like this, multiple reflection reaching to the receiver. So, we got to take account of the reflected sound also, and there are infinite number of reflections actually. There are infinite number of reflections in within an enclosure, right, within an enclosure. Now, here the absorption is important, just as we are talking about, because whatever is not reflected we consider is absorbed by the enclosure itself, whatever is not, you know. So, if I have an opening here, let us say if it was an opening here, reflection would have been 0, it would have, that ray would have gone out. So, that is sound within an enclosure. So, we got to look it into this manner, right. So, it is in fact this is what the source, you know. So, you have a source, let us say source, the receiver, and what is happening, there is only one direct sound, one ray of direct sound, and there are infinite rays of reflected sound, which can be one reflection after first only one reflection or after n reflections, right. So, actually if you see, sound travels different path, direct sound travels least path, while reflected sound travels longer paths. So, they will not reach at the same time, reflected sound will reach somewhat later than the direct sound, right, in time frame. So, in enclosure this aspect has to be taken into account, because sound will be reflected and they will contribute to the, I mean, either good sound or noise level. If you do not like it, then it is noise, but the diagram that I am showing so far, they are all auditoriums or similar sort of situation. You would like that to reach actually, you know, more sound to reach at the rear of the auditorium. On the back side of a classroom, I like that maximum sound reaches there. So, sound actually, since it's now is a function of time, the intensity that I will reach, it will be found to the at the receiver end, intensity at the receiver end will be a function of time. It is, you know, if it is not, I mean, it is related to the time, with time it will go on changing the moment from the time I have put on the source. It is a constant source, let us say, having same, not a human voice, but a source generated at kind of an source I generate through a bit frequency oscillator sound, you know, I have and a speaker system. So, basically electronic oscillators can generate electronic signals which can be converted into sound through transducer, and speaker is something of that kind. So, I have a speaker which generates constant power at a constant frequency, ideal condition, what we call pure tone, single frequency pure tone, and then I just kept it in position. Now, if I measure the time versus level at a point, I will find that it is varying with time. It is not, the moment I put on the switch to some time, it will not be constant, it will take some time to reach a steady state. So, this is how it behaves. So, with time, growth and decay of sound, it is something like this, sound in an enclosed space. So, intensity of sound, if I measure, it will increase, because during the first phase only direct sound will reach quickly. Then there are infinite number of reflected sound. The one travels least after just one reflection, that will reach next, depending upon its distance it travels, and some sound will come much later. So, it will take some time to build up to a steady level. and if I keep my source on, then finally it will attain a steady value. So, this is the steady duration of the sound since its growth, then it becomes steady, and if I put it off, then also what will happen? Direct sound will go away first. So, therefore, there is a quick reduction of the direct sound, which is maximum. The reflected sound will go on reducing. So, decay of sound after source has been stopped, it will go like this. So, you see, this is the behavior of sound in an enclosure, unlike the noise in outside, where there will be I put it on, there is a phase lag, right, and then the sound increases, and if I am keeping the source on, it will just reach steady value, no reflected sound, just it will reach, so it might be a step function sort of thing. Suddenly you will find that it is reached, there is no reflection, it will just, there is a time lag, it reaches and remains constant thereof, almost step function like scenario, but here it gradually increases because some of the path will be very long, many reflections, and every path at every point there will be loss. So, there is a reduction, the delta values would go on changing every time, because after reflection the reflected sound, because there is some absorption at the boundary wherever it is reflecting. So, some absorption is occurring, and second reflection more absorption will occur. Every reflection there will be some loss of sound at the boundary, and finally you can, so we can now estimate it, actually very simply we can estimate it, model it. So, this is how the physical behavior of sound within an enclosure, right. So, where I want sound to be there, what I will do, I like to see, then even this continues for a long time, this persists for a long time. What we have seen is that sound requires some time to grow to the level at which a steady level, and when I put it off, then also it remains for certain period of time, it persists, and this persistence we call as reverberation. This phenomena of persistence of sound after I have put off the source is called reverberation. Reverberation is a reverberation. So, this is the phenomena is known as reverberation. So, you will have actually, that is why I calling something like a reverberant field. So, this phenomena of persistence of the sound beyond I have put in, this is essentially the reverberation, this is reverberation. How long it persists? Now, supposing I have lesser absorption at the boundary, it will require longer time to decay to a nearly 0 level, longer time to decay, because absorptions at it will like if the absorption is high, after one reflection the value would come down to significant value, but if the reflection is less, I mean absorption is high, sorry, if reflection is high then it will come down, but if reflection is less then it will go to second reflection, maybe nth reflection and so on and so forth. So, phenomena of persistence is related to absorption of the surface, we will see that. Now, there is one more thing. Yeah.
So, why the auditoriums are dome shaped?
We will come to that. We will come to that. Not dome shape, but we will see the best shape of auditorium. We will see that actually, right. Okay. Now, there is one more point I would like to mention. When we are looking at noise outside, we are treating most of the time source as point source, because the distance of the receiver will be relatively large compared to the source, and I said that it should be 6 times or so. In a space, enclosed space, very close to the source, it is actually near field. If I plot with log r, you have seen that 20 log r. So, near field is where the source is not point source. For point source, LP is so many things equals to so many things minus 20 log r, minus 20 log, say some constant K1 minus 20 log r, that is what I have seen. So, if I plot against log r, for a point source it will be linearly varying with log r, right. But practical sources, so for example, if it is a large surface, this is surface and close distance, sound will come from all the points, then it is higher than more than that you would have got otherwise if it was a point source. So, for a line source, planar source or anything practical sources, you will have some higher values, right. So, this field we call as near field, near field. In a enclosure, this sources can be near, while in noise usually sources are far off places, but if it is near, then you will get normally higher than what we have talked about earlier, that it is equals to LW plus DI minus 20 log R minus 11. No, it will be more than that actually. So, this is what it is. So, this we call as near field. Then beyond this is all our far field, where I can treat it as a point source. Beyond that is far field, where I can treat it as a point source, and in the far field log R, it is proportional to log R. But if I go, there is a distance beyond which reverberation sound, that is if it is within an enclosure, reverberant sound will actually overtake the direct sound. If the source and receivers are very close, 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 right, source and receivers are very close, if the source and receivers are very close, direct sound will be dominant. Value of direct sound will be much higher than the reflected sound, If the source and receivers are sufficiently large distance, then direct sound will reduce, but reverberant sound might be same, because it is coming from after infinite reflections. It is coming after infinite reflection. So, what we call this field, where this point we call as room radius. I will define this later on. But this field where reverberant sound is more or comparable to the direct sound, we call it reverberant field. We call it reverberant field, right? We call it reverberant field. We call it reverberant field. Okay. So, this idea is fine. This idea is fine. Okay. So, this is how some definitions of the field, etc. Supposing I am adding 60 dB plus 60 dB sound, two sources are there. From one I get 60 dB, from another I also get 60 dB. How much it will be the total noise level? It will be actually how much? Let us see, it will be 63. How? Because 60 dB would corresponds to 10 log. If I take intensity or pressure level, does not matter, intensity level divided by I ref. So, intensity corresponding to this, and this is 10 log. So, I 1, let me call it. So, I 1 is equals to I 1 by I ref will be equals to 10 divided by, so 6, 10 to the power 6, am I right? Because 10 log, it was 10 log. So, I by I ref reference would be how much? 10 to the power 6, 10 to the power 6, am I right? 10 to the power 6. So, how much is I then? 10 to the power 6 into 10 to the power minus 12. I can, so this is nothing but 10 to the power minus 6. So, if two such sources are there, what will be the total intensity? Twice into 10 to the power minus 6 divided by 10 to the power minus 12 is I ref. 10 log of that, 10 log of that, you take 10 log of that. So, 10 log of 2 into 10 to the power minus 6 divided by 10 to the power minus 12 will be nothing but 60 dB plus 10 log 2, 60 dB plus 10 log 2, right, am I right? 60 dB plus 10 log 2, all this I can erase now, let me put it like this, right. So, which will be equals to, I can write it like this, I can write it like this, this will be equals to 10 log 2 plus 10 log 10 to the power 6, because minus 12 will go up there. So, which is nothing but 10 log 2 plus 60 dB. This is 60 dB, because if you take this, and this is what 3.0 whatever 10 or whatever it is. So, about 63 dB. So, if you same double dB, it is only increased by 3 dB. So, when you are this plot was related to dB, this plot was related to dB. So, I am writing SPL dB. So, dB, if this is the intensity is much higher, it will not, by adding say 50 dB to 60 dB is no good, because it will be still 60 point something. 60 and 60 is 63, 60 and 50 might be 61, and 60 and 40 would actually mean, so whichever is higher that dominates, because 10 to the power minus, 10 to the power, we said 10 to the power minus 6 was the intensity, I1, right, because I divided by I ref was 60, so 10 to the power minus 6 you will get. Now you add this to 10 to the power minus 8. So if it makes no sense actually, it hardly any addition would be there. So dB addition, higher one always dominate. That's what I was saying. Let me do it again. Supposing I am adding 60 dB to 40 dB, 60 dB will be 10 log I divided by 10 to the power minus 12, right, and this was 60. So I came out to be 10 to the power minus 6, you remember, 10 to the power minus 6, right, 10 to the power minus 6, because this will be 10 to the power 6 and this is minus 12, so comes out to be 10 to the power minus 6, and if it is 40 dB, it will be 10 log of I2 divided by 10 to the power minus 12. So this is 10 to the power, log of, basically log of I2 by I ref is equals to 4, right, because 40 divided by 10 is 4. So I2 is how much? I2 by I ref will be equals to 10 to the power 4, and I ref is 10 to the power minus 12, 10 to the power minus 12. So this has to be, I2 will be 10 to the power minus 12 multiplied by, 10 to the power 4 it was. So I2 will be then equals to 10 to the power minus 12 into 10 to the power 4, which will be equals to 10 to the power minus 8. Now you add I to the power 10 to the power minus 6, 10 to the power minus 6 plus 10 to the power minus 8. Actually this value will be quite small compared to this value, So therefore if you divide this by I ref now, effect of this one is practically not there. So if you add 60 to 40, it would be 60 plus very small value. So that's what is happening here as well. Since we have plotted decibel values, reverberant field, if it is much higher than the direct field, it will be practically showing a constant value. It will practically show a constant value, right? Practically show a constant value. So that's what it is. So that's what. Now let's look at this scenario. We define a term called energy density. Reverberant field. What is reverberant field? Let's understand what is reverberant field. Reverberant field means it's there anywhere in the room, the value is constant. That's what we are assuming. Multiple infinite number of reflection. So if I take any point in the space within the room, within the enclosure, sound will reach after multiple, I just for the sake of it, let's say I kept the direct sound out. So put a sort of a, such that it is all reflected sound, a diffuser around the speaker. Diffuser around the speaker. So it goes all around the place. All around the place, no direct sound is reaching. Then if I take any point or another point, ideally speaking, it will show same decibel level, because every point only the infinite reflected sound will come, and infinite everywhere. Therefore, this reverberant field has largely a constant value. It is reality, it will not be. Reality will find where there are, absorptions are not same at all surfaces. Where there is less absorption, actually you might find the field slightly, decibel level slightly higher. Where there is higher absorption, it might be somewhat lower. So everything put together, ideally we assume that reverberant field is constant, uniform. So we call it diffused, uniform diffused field. Uniform diffused field, because it is diffused, coming from any direction, not specular. Specular means what? Like, something like a mirror. Angle of incidence is equals to angle of reflection. That will get clear. We also talk of lighting and illumination a little bit. So this is diffused, means coming from any direction, anywhere. So you take any point in the space that will have, for example, any point in the space anywhere in this space, it will have same reverberant field, that is what ideally we are assuming, and value of this intensity value related to reverberant field will be constant. That is what we are saying. So, therefore, we can talk in terms of energy density of the reverberant field, which is energy per unit volume, energy per unit volume. Now, supposing I consider unit area, right. So, energy contained in unit area, and sound is travelling normal to this, right. So, energy density will be energy, area and the distance. Now, energy density is defined in this. So, intensity here is I, which means the power per unit area, energy that is passing through this area A in unit time, right, that is intensity, unit time through that unit area. So, if area is A, I into A is the energy that will pass through this area in unit time, right. So, that multiplied by energy density is energy per unit volume. I am saying I into A into C, sorry, I is watt. So, I want to find out joules per meter cube. So, this is actually watt means joules per second. So, multiplied by T, travelling through T time, and C is the distance which it travels in T into, it can be related to I into T is in 1 second actually, per second. So, how do I define I? I was essentially energy per unit area per unit time, right, per unit time. So, energy per unit area per unit time, right, and volume, if I want to find out in unit volume, that is right. What is the volume in T time? Volume it has covered through T time, T into C. So, basically the length would be C. So, I energy density, energy per unit area per unit volume, because T into C is the distance it has covered through T time. This distance multiplied by the area is the volume. So, energy content E divided by that will give you per unit volume. So, from that it follows that E etc is I by C is actually energy density. I by C is energy density. I is watt per meter square, right, and C is meter per second. So, watt per meter cube into joules per meter cube it will become. C is the velocity of sound. So, this is energy density. We define a term energy density, we define a term energy density, right, and now any point if I consider, that can be treated as a source. Any point in the reverberant field, I am dealing only with the reverberant field now. So, any point in the reverberant field or in the space anywhere, say somewhere at the building, I mean somewhere in the space, I can consider a dV volume, and that can be treated as a source. So, small dV volume if I take, multiplied by the energy density, which sometime we define in terms of epsilon or E, sometime we might define in terms of epsilon, some books will define it, So, I think that is what I am doing further. So, this would be energy density multiplied by this is the energy contained in that space, small dV volume, energy contained in that space in small dV volume in a constant reverberant field. Now, from this source, I want to find out how much of it will actually from the reverberant field, how much of it will reach the periphery wall. So, I consider a small portion of the wall, ds element in the wall or ceiling or wherever it is, somewhere in the boundary, So, this is dV element, somewhere in the boundary it reaches, right, and I can define, say this is ds area of this is known. So, I can define something called, it will reach over how much it reaches over the boundary area I want to find out. So, I can define something called, we know something called solid angle. So, if this is making a solid angle right? Angle is for an arc divided by distance. Arc divided by distance is, like if you call it length divided by r, angle is given by that, but solid angle is given as area divided by distance square. You can understand that, because how do you define actually the angle came from a circle makes pi into diameter pi d, pi angle. So, ratio of the total perimeter divided by diameter is constant, that is pi, that is pi, So, that is what you call as angle. Therefore, you take a small arc, you can define the angle in some ratio of this pi, right, pi by 2, pi by 4, pi by 6, etc., etc. That is how the angle basically came into being. Now, if you look at sphere, we are talking of circle, sphere equal distance from the point, then it has got pi d square, right, pi d square is the surface area. So, if or 4 pi r square is a surface area, right. So, we call 2 pi angle is made by the the sphere, circle makes 2 pi angle, we called it 2 pi. By same token, we divide by r square, the 4 pi solid angle is subtended at the center of a sphere. 4 pi is the solid angle, which is constant. So, surface area of a sphere divided by the radius square is a constant, and that is 4 pi, and that 4 pi is a solid angle subtended by a sphere at its center. We call it 4 pi steradians instead of radians. So, from this one, if I assume take a small ds angle, that kind of a conical volume which is there, through which the sound will actually reach here. Sound will be, this will be emanating sound, and it will reach here through those solid angle. All the sound wave that is travelling through that solid angle will be reaching here, right. Earlier we have seen the spherical wave front. So, we took a point source, and it goes around all 4 pi. So, distributed over the surface area, same thing, that is why you take the area part here. So, this is almost we can treat as a point source, and this is the ds area. So, what is the solid angle it will be subtending? ds divided by the r square, ds divided by, and this we call as d omega. So, d omega is nothing but ds divided by r square, ds area divided by r square, the distance square is nothing but omega. D omega is a solid angle, small solid angle it subtends, right. And how much of the sound will how much of the sound will reach here actually, that I can find out. Consider this kind of a surface, because there are if I look at this, all this, I mean I am interested in how much sound reaches here. Now, I have taken a point. If I take larger area, instead of point small dB volume, I take larger volume and integrate, then I will get the total amount of sound incident on it or impinging over it, total amount of sound impinging over it. Now, what we do is, we do not take like all rectangular areas, but it is coming from all direction radially, from this direction, that direction, etc., radially from all direction. So, what we do is, we take a hemispherical situation, right, hemispherical volume. If I am interested in t time, then diameter of that or radius of that hemispherical one will be t time, I said c into t. So, I can integrate from 0 to c into 2, that is the sound that will reach, anything beyond will not reach, because it will come radially from all direction. So, to do that, what we do is, we simply take a torus volume of this kind, we take a small torus volume of this kind, consider the chord circle, there is a large hemisphere around it, because bottom side is not there. So, I am talking of hemisphere. Take a chord circle and a small element in the chord circles, right, small element in the chord circle. This is the radius of this one, this is the dr, because it is going outwardly, dr is going outwardly, right, this is dr. This I can find out knowing how much angle it makes, we will come to that again. So, this is dr, this value I can find out, and I can actually take, if I take a small volume, then this dimension also I should be taking. So, this dimension d phi, I call it d phi, this is d theta, because it is making an angle theta here, this one, this is my ds, I can consider it is making an angle theta here, d theta. So, d theta into one dimension will be d theta into, this one would be one dimension will be d theta, this will be dr, this will be dr will be radially outward, this is vertically down. So, if this angle is theta, this height will be r d theta, this height will be r d theta. Do you agree with this? If I take a cubical volume, let me just again erase this out quickly, erase this out quickly. So, this height will be nothing but it will depend upon what angle it is making here. This distance is r, this angle, if it is elevation angle, is altitude angle, remember if it is theta, then it will be r d theta, right. So, this height will be r d theta, right, it is clear. Radially going outward is dr, and this one will be how much? It will be d phi, along in the plane. If I put it in a projection into the ground, like azimuthal angle. So, one angle will be azimuth, another is kind of something synonymous to my altitude angle, and third one is dr. So, I can actually find out the volume in terms of r d theta, d phi, right, and dr. Now, d phi will be how much? Because it is, this is, so any distance I take here would be basically I am calling it as d phi multiplied by this radius. I am taking from a torus. So, this distance, any distance here, part of, or any distance along this line, if I know this radius. Now, this radius is nothing but, if this the distance is r, then r, yeah. So, depending upon the theta, so I can find out in terms of r, this will be r, this is r. So, this is vertical one will be up to the center will be r cos theta, r sin theta it would be, right, it will be r sin theta because it is opposite to the angle. So, r sin theta will be one term, this is related to d phi, r d phi I was talking about, r sin theta d phi, and then another one will be simply dr, and another will be r d theta. This vertical height will be simply altitude angle changing by d theta. So, if you look at these products, it will come as r square sin theta d theta, r square sin theta d theta d phi dr, right. And if I integrate it from 0 to c t, or 1 second if I am 0 to c, that is all the sound that will be reached here. We will derive this, we will look at this again in the next class from this point only, right. So, we will start from here again. So, you find that dV is equals to same thing that I was talking about. So, we will start from here r square. So, we have to stop here.